So we're in chapter 15, section 7. The last section's on hydrolysis and buffers, two subjects here that kind of go together. And so it basically starts off about talking about salts. It says acidic or basic salts and hydrolysis. So one of the products in a neutralization process, when you're neutralizing acids and bases, is salt, of course. And soluble salts are completely dissociated in the aqueous solution, but many salt solutions are neutral. They're pH 7. However, experimentation reveals that solutions of many other salts are basic or acidic. So there must be a reaction then between the water and the ion in the salt to produce. So you must have, if you're going to have a pH of other than 7 with the salts, there must be something going on with hydrolysis going on in the water to produce the OH negative and the H3O instead of H2O. So this is acidic and this is basic. So in the midst of a salt solution. So otherwise the solution would be neutral. So we find out there must be some hydrolysis of the water, making it slightly acidic or slightly basic, right? And so now we have this hydrolysis, since it involves the splitting of water molecules, it's called splitting. So when you think of hydrolysis, you're thinking of water. So now they're talking about salts and that were involved in the water, that some salts are a little bit acidic or a little bit basic. They must be being influenced by hydrolysis, which is hydrolysis has to do with water. And of course, since the salt is a product of the acid and base, here we have the salts of strong acids and strong bases. We're going to examine these salts. And there's a table here, table 5.5. Let's see, where's that table? Right here. 5.11. Well, let's go back. So many classify salts according to the strengths of acid and bases. Okay, if we go back to table 15.5, all it tells us, remember we went through the strengths of how strong an acid is. And if we go back to that table, let's go back, just look at that really quickly so you can see that table. See if I can get that table going here. It's quite a few back here. The strengths. Okay, that's pH. Let's go back to the strengths. 5, 4. Go quite far back, sorry. One more. Let me go back. Here's the we talked about strengths. Here we go. Remember this here? So the table here, it tells which are strong acids and which are strong bases. And they're always opposite, because in reaction, they conjugate, they equal out each other. So we have the strong acids being up here, of course, hydrochloric acid being nitric acid. All these are really strong. The hydronium ion in itself, all these are very, very acidic. And then we look at the bases, and what do we see in the bases? Of course, the hydroxide ion down here is very basic, and then we see, the carbonate ion, ammonia all of these are very, very strong bases. And so that's what we're going to look when we put them together, how to see which ones are strong and which ones are not so strong in producing this in the salt. So let's go back to that last section. Sorry, I have to go back quite a while. Here we go. Right here's where I want to be. Okay, so here we have the salts of strong acid and strong bases. So we know, okay, that we have a strong base. Sodium hydroxide is a very strong base. NaOH, OH being that, making it a really strong base. And then we have a strong acid here, as the acid is, as these are strong base and a strong acid coming together in a salt, and so we can see where the salt's going to come out. We have Na being salt, coming out. The salt of strong bases, but a weak acid And you can see the strong base combining with the weak acid here. We have the salts of weak bases and strong acid. This is a weak base and this is a strong acid coming together here. And then we have the salts of weak acids and weak bases coming together. You can see, okay, what we have here in this you're thinking, well, why do we have this? It's because here we see they're coming together. As they come together with a strong acid and strong base, they're just going to come together and they're going to basically make the salt here, and there's going to be no residual, right? There's no hydrolysis of water or anything. Just basically this happens. And this is a salt of a strong base and weak acid. Some weak acids here, the strong base and the weak acid, and it's doing the same thing. It's just coming together for the salt. And then we have the salts of a weak base and strong acid. And you can see how this now, okay, so now we have an arrow coming around this way. So we're going to have some hydrolysis here in what they're showing here, as we have this weak base and a strong acid coming together. And then we have weak acids and bases coming together, and we have arrows going in all directions, because in the midst of this, you're going to have some seep into, into water. There must be something else going on. So these properties determine whether a salt solution will be acidic, basic, or neutral. So we're looking to see, is this going to be this one, is it going to be a neutral, like some of these, or is it going to be influenced and be a little bit basic or acidic? So it says here, strong acids have very weak conjugate bases, and strong bases have very weak conjugate acids. When you talk about the word conjugate, it's what they make. If you're going to conjugate something, you're making or putting together something, right? And so strong acids, they end up giving out very weak conjugate bases, putting together, and strong bases, weak acids. So if you have a strong acid and it ionizes completely when it's dissolved in water, then it ionizes completely at that point. Then with water, the water is going to be negligible, and so it's basically going to just produce that salt. So it's not going to go under any hydrolysis at all, changes like this case with the strong acid and the strong base, because they just make very weak conjugates, and the conjugates are not going to matter. So, and then here, similarly, the cation of strong bases has no tendency to react with water. So a strong base or a strong acid is not going to react to the water. And so you're going to have more of a neutral salt. So the strong acids and strong bases are going to produce a neutral. So the anions of strong acids and the cations of strong bases do not hydrolysize with the water to make acids or bases, so they are very neutral. So say you take salt water, or the salt coming out of water, sodium chloride. That's a good one. It's not going to be very acidic or very basic. It's going to be not basic. It's going to be neutral. So because the strong acids and strong cations do not hydrolysize. But weak bases and weak acids can conjugate bases and acids that are strong enough to react with the water and form basic or acidic solutions. For example, this is with fluorine. So you have a weak acid and it's hydrolysizing at this point, as you see, and you're going to have it as it's hydrolysizing with water. You'll have it as it's going through the production. Here's the equation for it. And you'll see that the ammonia ion is a conjugate acid of the weak base and ammonia, and will react with water to a certain extent to produce some ions, acid ions, which are H3O. These are the acidic ions, and thus they form an acidic solution. So hence, let's find out what hence means. So cations of weak bases hydrolyze to form acidic solutions, and anions of weak acids hydrolyze to form basic solutions. So what they're just saying here is that weak bases and weak acids will react with water or hydrolyze with water. And this hydrolyzation process will produce a little bit acidic or basic salts. So it's a long ways to go for just the end result, as I went through all that. But that's what your book is trying to show you here. So basically saying if you take a strong acid and a strong base and you put them together, you're going to get a salt. And that salt is just going to be salt, neutral. It's not going to hydrolyze with the water and make the salt acid or base. But if you have a weak acid and a weak base, or in the line of some of those, you're going to have it's going to hydrolyze with the water and produce a more acid or a more basic salt. So we're talking about the salts. How do they get acid salts and basic salts? It's because of how they're hydrolyzed with the water. So, so here it says, returning to our examples of the 4 types of salts, we have sodium salt is the strong acid and the strong base, sodium nitrite there. So in the midst here we have this ion hydrolysis so that the sodium is a neutral. Anyway, going on to this same thing, here we have ammonium chloride and we have baking soda, and you can see how baking soda is now going to be a salt, but it's going to be a salt that's very basic. In fact, if you take baking soda, you can mix it. As you mix it, will be a good neutralized. Baking soda will neutralize acids. And so here we have acidic ammonium chloride. Here is an acidic salt. So how they became that acidic or that basic has to do with how they hydrolyzed with water, and coming from weak bases are weak acids instead of strong weak acids to make this. So that's just telling how salt becomes acidic, because usually salt should be neutral, right? How salt becomes acidic or basic. So let's take this table of hydrolysis of salts. So you have a salt contains a strong base, a strong base or cation of a strong base. We're talking about ions now. So it takes the cation of a strong base and a strong acid. Strong bases and acid make the salt neutral. This is just what we talked about. You take a strong base and a weak acid. The strong base here makes it basic because it's the base is strong. And now you have a strong acid in a weak base. So you have a strong ion of the acid in a weak base. Of course, the acid's going to be strong, so the salt solution is going to be acidic. But if you have a weak base and a weak acid, in that situation, you could have acidic, basic, or neutral. So here is the hydrolysis of salt solutions. Of course, strong base and strong acid is neutral because it doesn't hydrolyze. The hydrolysis doesn't happen, so much. But as the weaker an acid, it's going to be, if the acid's weak, the base is going to be strong. If the base is weak, the acid's going to be strong. And then we have weak, and weak could be all different kinds. So with the 2 weaks, weak acid and weak base. So I hope you understand that. So let's go on here. In summary, the aqueous solution of a salt will take on the characteristics of the stronger substance, acid or base, from which it is considered to have been formed in the neutralization reaction. That's just what I went over here. That's the summary. There's a good summary on this table of just what I went over for the last, 10 minutes, is how hydrolysis happens. So if you have an ion, 2 ions that are very strong, it's going to be more neutral. So this is tell whether the aqueous solution of calcium acetate is acidic, basic, or neutral. So here's the formula of calcium acetate. And here's the cation, which is 2 plus 2. And it is the cation of a strong base, OH, 2. And the anion is the anion of the weak acid. So thus this salt is a strong base and weak acid. So we have a weak acid on one side that will turn on to a strong base here. So then we're going to know that it's going to be more basic if it's a stronger base. So it'll always have properties of the stronger component, which would be the base in the situation. So we're going to go on to buffers, and we're going to talk about the buffers in our blood. And that's going to be end this chapter. But I think it's really neat to end this chapter with how our body, and our blood and our plasma and our electrolytes in our body, and how they actually equalize out and set our blood plasma into such a neutral, the neutral pH. Otherwise, if we had too much acids, we're going to have problems with our health. Or if we have too many basics or bases in we're going to have problems in our health. So I like it here. It says where it's important in many situations for the pH of a solution to remain constant, right? So the pH of your blood plasma should be maintained between 7.35 and 7.45. That's a very narrow range. Isn't that God? How God maintains our blood plasma in such a narrow range, despite everything we eat that's acid, Almost everything we eat it has acid value. I can't think of anything that's not, from coffee to citrus fruits and everything else acid, but our body keeps our pH level in our blood normal. So how wonderful, that God can do this. Because if the pH would vary just a little bit and falls between either above 7.8 or below 6.8, we would be very sick, or we could die at that level. So there's so many processes in our bodies that buffer, they're called buffers, to neutralize, eliminate the pH to get out of range. So it's constant. Because foods would make our bodies either acidic or basic. So the regulation of pH is accomplished by what we call buffers. These buffer systems in our body work very hard and keep our pH, our acid level at neutral, our acid basic level at neutral level. And that again is so amazing, so wonderful that our body would do such a thing. So, and here's some the equations here. According to Le Chatelier's, remember Le Chatelier's have to do a shift. It's how a buffer system would shift to one side. If we have too much acid, it's going to shift to one side. So here's acid added acid molecules. Acid is hydrogen H3O, and this will push it to the left. Too much acid, it's going to go to work and push it to the left side. So, and that buffer it to the left so that it will, right away our body wants to equalize everything out to keep our body in the right pH level, so that we'll have neutral blood, right? And our body will not be affected by the strong acids. So you put more acid in it, it's going to go to the left. So here we have the making more acid here. It's going to push it to the left to try to get rid of, buffer out that acid. So if, on the other hand, if you add small amounts of base, too much base is going to go to the right. So I think, even in politics, things go to the left and things go to the right, right? If you have too much acid, I think this is the way I thought of it. If you have too much acid, in liberalism, too much acid, acid just causing so many problems, it's going to go to the left, and then if it's too much base, too much like rules and regulations, base, goes to the right. So that's how I remember it, kind of, But anyway, it shifts. And these are just buffers. When they shift to this area, they're just drastically trying to shift your blood back to normal. That's what they're doing, because they have either too much acid or too much base in them. So you can see how you add this, basically saying adding more of the hydrogen, which is the acid, the equilibrium then go from the left, and then it goes back to the right, and then it goes back to the left. So this is how buffers work. So it's kind of neat to go through this. I'll let you read this over on yourself. But this Le Chatelier, whenever you think of Le Chatelier, is that I always think of Chatelier as shift. It's going to shift the equation, which it's going to do. It's shifting right away to get rid of the acid of the bases. And here's the arrows, means that more is going to the right here, and the less is going to the left. You see the arrows? More is going to the left and less to the right. So you're going to push to one area as you're trying to get rid of these are the ones you're trying to get rid of. These are acid molecules you're trying to get rid of. So you're going to push it to the left. You're trying to get rid of them. And these are, then after it comes to that point, you see you have, okay, now we need to, the shift's going to go, on the other hand, you're going to add the base and it's going to shift the other direction. So it's kind of like shift, trying to shift get into equilibrium. So a buffer may be defined as a solution that keeps the pH relatively constant because it contains a weak acid and its conjugate base, or weak base and its conjugate acid. So a buffer system usually has a weak acid or weak base in that to buffer things out. And this is in our blood. We have certain buffer systems in our blood. So, and also in other areas too. When you think of buffering, there's other buffer systems besides just in our blood. But anyway, this whole buffer system, okay, right here, how God has designed the bodies of humans and animals with amazing capacity to maintain the pH within a narrow range. This is accomplished in our bodies by at least 3 buffers, along with a host of other mechanisms. So we have 3 buffer systems. What are these buffer systems? You can read through this, but the first buffer system related here is the bicarb buffer system. And so this bicarb buffer system, let's see. Let me go over that here. Here we go. Blood buffers. I was going to show you the exact here, but anyway, let's just go over this kind of. So the carbonic acid is probably the most important buffer system. And this carbonic acid you see is H2CO3. So, and as it's combining here to get rid of the carbonic acid, it's a weak acid there. It's metabolizing and it produces, producing this weak acid. The acid adds to the blood to neutralize the blood by a bicarbonate, and this shifts everything to the left. Such a beautiful design here. So here you have it as for the bicarbonate system, back and forth as it's buffering out our blood. Number 1 is the carbonate. How do we get this bicarbonate in our body? It's from the CO2, because our body produces a waste product. We breathe out carbon dioxide. So carbon dioxide is actually important in our blood to act as a buffer. Isn't that amazing? As we're breathing in, oxygen, taking oxygen in, and it goes through our heart and everything, and then carbon dioxide metabolizes out and we breathe out carbon dioxide, but also some of the carbon dioxide turns into this buffer system with this weak carbonic acid in our body that uses to keep our blood within the neutral pH range. So how amazing. So that's number 1 is the bicarbonate from carbon dioxide actually system. A second blood buffer is the phosphate buffer. And this too is another type which keeps us in equilibrium. And so you see that phosphate reaction, which reacts with the bases, with the ion, H3O ion, hydronium ion here, and causes this to ionize and helps to buffer out. So number 1 is the bicarbonate, or the carbonic acid with carbon dioxide. The other now is the phosphate buffer system. So, which is pretty amazing. And then we even have a third buffer system. And this buffer system is in our proteins that are present in our plasma. And here is the COO negative in the protein group here. So we have this protein, and this shows the equation here as their protein acting on as a buffer system too. You see how it's buffering out, which can act as protein acceptors and proton donors. So you have both acids and bases being neutralized in this situation. And this is such an amazing design that there's no way someone could just figure this out to make our body so amazing as God has, with these backup buffer systems. First, we have the carbon dioxide bicarb buffer system here, carbonate buffer system, which is our most important. But if something happens here, we also have a couple other buffer systems with the phosphate and onto our protein buffer system with our proteins and the backup systems. So our amazing God has put together such amazing ways that we can stay alive, that he has brought life, and now our body is definitely fearfully and wonderfully made. So how amazing. When you think of acids and bases and the way they react in our world, it's such amazing that God would design it in such a way to keep everything in such a neutralized state. When you think, and you think of other planets that are probably hugely acid or hugely basic, or all of these, but because of our planet Earth, too, in the midst of how God has all of these different ways to take acids and bases and neutralize them out so that we could live here even. So what amazing God we have.